Great. So thank you so much for being here. I'm really excited for this last of the talks of our Young Professionals Lightning Talks. This has been wonderful, and I'm really looking forward to ending up our presentation. Are my slides there? Let's see. There we go. OK, cool. So in 1990, the Voyager spacecraft turned around and took a picture from the edge of the solar system. It captured a beautiful image of the Earth that has been known as the pale blue dot. Who here has heard, seen of, the picture? Cool. It's a common theme that we all turn back to as lovers of the space world. But my favorite picture that is referenced as that was actually taken about a decade later, when the Cassini spacecraft turned around at Saturn and took this beautiful picture that is my desktop background at Yale, where I'm a Ph.D. candidate in astrophysics. I love looking at the sweeping rings of Saturn that go across the top, because Saturn is my favorite planet in the solar system, and looking at that dot that is our Earth. That dot has everything that we know on it, and when I'm in the midst of proposal writing, when I'm trying to debug my code and I'm super stressed because it won't work, when I can close down the internet browser and look at this picture, it always calms me and brings me back to why I do this and why we all get interested in space to begin with. So that dot, it's me, hi, I'm on it, and you and everyone else, and bonus points to anybody who got the Taylor Swift reference just there. But that dot has all of our favorite music, it has all of our pets, it has all of our favorite food, it has all of our favorite TikTok stars, all your favorite movies, all your favorite books, all in what's barely a pixel on the screen. But that Earth is only one of 5,272 known planets as of last Friday. And it's an example of how there are so many other kinds of planets in our solar system. So our solar system has 8 planets because, sorry, Pluto is still not a planet. And we have these beautiful images of all 8 planets because we can send missions to them. We can capture beautiful, detailed pictures of their surfaces. We can learn about their interiors. We can measure earthquakes, well, Marsquakes on Mars. Like, that is really cool. But we can't do that for these 5,000 other planets. And every time we look at this system of 8, it's only one realization of a planetary system. So I want you to stop and think about what would you put in a planetary system if you were making one. One of the earlier talks really set us up for this. If you were creating your own planets, and if you were taking it a step further and creating your own planetary system, what kind of planets would you put in it? How would you orient them? What kind of architectures would you set up? So we're going to try that, and we're going to play a game called Make Your Own Planetary System. We're going to start by picking a star. So there are a couple different kinds of stars you can choose from. There are more than are listed here for sure. But we're going to start by making our own solar system under this framework. So we're going to pick a sun-like star. Next up is choosing our planets. This is where I have a lot of fun because I'm an exoplanetary scientist. So I look at all these exoplanets every day. And while there are planets like the ones in our solar system, kind of, there are also other ones, like the hot Jupiters, that are planets that have years that are about 10 of our days. They orbit super close to their stars, and they're Jupiter-sized, hence the name hot Jupiters, because astronomers are clearly very creative at naming things. If I was to pick the planets for our solar system, I would pick 2 sub-Neptunes, which is the broad category that encapsulates Uranus and Neptune. I would pick 4 super-Earths for our rocky planets, and 2 gas giants for Jupiter and Saturn. So we've got our star, we've got our planets. What's next in a planetary system? Well, how are we going to put all of these things together? The first step in that is choosing what we're going to call the tilt of our star. So to think about the geometry of that, I want you to think about looking at a solar system from the top down. So here you're looking at the star in the middle and the planets orbiting around it. And then you're going to move 90 degrees and look at it from the side. And you're going to have your star in the middle and your planets orbiting around it. And run with me here for the sake of analogy. Imagine those planets are pieces of butter moving around on the top of a pancake. If you stick a toothpick in the top of that pancake, that toothpick is the axis that our star is rotating around. You can imagine putting the toothpick into the side of the pancake, and in that case, your star is on its side with respect to the plane, or the pancake, that the planets are orbiting on. If we formalize this by putting in a set of axes and then sticking in our toothpick at an arbitrary angle, That angle is our star's tilt. For the solar system, this tilt is about 2.7 degrees. So that is referred to as very well aligned. And that matches our traditional understanding of how planets form and how these systems evolve. Our final element are tilts for our planets. So every single planet has a tilt in relation to the plane, the pancake that the planets are orbiting in. For Earth, that tilt is about 27 degrees. And we would need to go through and pick a tilt for every single one of the planets in our solar system, which are all shown here. My favorite is Venus because it kind of is like upside down and goes around, so that's kind of fun to think about from a geometry perspective. So we have this one realization of a planetary system, but what I do is spend my days researching all the different variations of these planetary systems that we can see in the universe right now. Currently, with our 5,000 planets, I'm able to use data from NASA's missions like TESS and data that I collect on the Keck telescopes in Hawaii to be able to understand what these planetary architectures look like and why that matters. Like, why should we care that there are these systems out there? And ask, is the Earth unique in the universe? That's the guiding question for my research, and it brings us back to that reference of our little pale blue dot in the Cassini image. So rather than doing that exercise 5,000 times, I'm going to skip ahead a little bit and show you all of these planets that we know of on a mass period plot. It looks like it's not quite showing up right, but that's okay. The mass scale is Jupiter masses, so if we put our Earth on this, it would be where the dot appeared, not where the text appeared. And we would have a period of our 365 days and a mass of 10 to the minus 2.5-ish Jupiter masses. If you apply your pattern finding skills to this plot, which we as humans are pretty good at, you should be able to spot 3 different populations. These 3 populations are interesting because they are the broad classifications of exoplanets that we have right now. And only one of these 3 populations is a kind of planet that we actually have in our own solar system today. So the first of these populations is the hot Jupiters and the cold Jupiters, so 2 of them. The hot Jupiters we talked about briefly earlier, which are these planets that are Jupiter-sized, but they're super close to their stars, so hence really hot. They were the first exoplanets to be discovered because they're massive and they're very close to their stars, which is easiest to find. The second population are these cold Jupiters. Cold Jupiters are farther out from their star, but also Jupiter mass, and yet another example of the creativity of astronomers in naming planetary populations. This is where our Jupiter would fit into. So this is the one kind of planet that we have that's on this plot that's in our own solar system. Finally, we have the short period planets. These are the ones that I find most interesting because if we were going to go out and look for life, I think these would be where we would look. They're also really interesting because they have periods of about 10 days, which is a 1/7 of Mercury's orbit, and Mercury is the closest planet in our own solar system. So the fact that we can find so many short period planets but not see any of them in our own solar system suggests that we have an anomalously empty inner solar system. And breaks a lot of our planetary evolution models, which is great because it means that there's a lot more astrophysics to do. But it's a super interesting problem to think about because it suggests that our solar system is not the typical solar system in the universe right now. So if we are thinking about our parts of a planetary system, we have our stars we talked about before, we have these planets. We can also think about, for this population of 5,000, how many do we have measured stellar tilt for? And the answer is about 70. It's really hard to measure the stellar tilt for these planets. There's a couple different methods that have been applied, but they usually only work for large planets that are close to their stars, so the hot Jupiter population on this plot. I won't even bother to show you a plot of how many planets we know the planetary tilt for, because there are only about 4 out of the 5,000. Because if you think finding a stellar tilt is hard, finding a planetary tilt for a planet that is a long ways away from us, that is barely a dip in light, is quite a challenge. So here what I'm showing you is a scaled down version of a small handful of the 5,000 planetary systems, all plotted with the number of planets in the system, their orbits. They're all scaled so I can show them to you on one slide and have it be actually reasonable to look at. But I want to bring us back to our question. Is the Earth unique in the universe? We don't know. There are still a lot more planets to be discovered, so many more things to learn about planetary formation and evolution. What we do know is that the idea that we have some privileged position is challenged by the countless planetary systems that look nothing like our own and also look different from each other. This plethora of planetary systems helps to put our own solar system into context. And to me, Earth's precarious position in the universe becomes a little bit clearer. So as we here at SGx, the next generation in the space world, approach issues like climate change, gender inequities in the space world, education disparities, conservation efforts, all the sustainability work we heard about this morning, I want you to go into those conversations with planetary systems in the back of your mind. Remember the perspective that this kind of plot, this kind of depiction of all the other worlds out there can bring as a reminder for how important it is that we do this work here for our own planet. The Cassini image of Saturn and Earth is humbling because it reminds us how fragile and precious our own planet is. And as we go forward to face the greatest challenges of our generation, let's keep that perspective in the back of our mind and let it guide our actions. As we go forward to try and make a better world for our planet and all the life on it and all the inhabitants of it, we can bring this perspective of planetary systems with us to help put everything that we do into this broader context. The search for life beyond Earth is going to continue. We're going to keep finding new planets. We're going to keep going out and hunting. And as we do so, I hope that we can bring this awe and wonder that makes us ask the question, is the Earth unique? And the perspective that comes from asking that question with us. Thank you.